Ponente. Hello and welcome to today's CAP seminar, which will be held by Juan Manuel García-Ruiz. Juan Manuel is a research professor of the Science Research Council of Spain, CSIC, at the University of Granada. He is an expert in crystallization of minerals, drugs, and proteins. He has led crystallization projects in space, participating in more than 30 European and Japanese laboratories. And at present, his main field of study is the phenomena of self-organization and self-assembly in biological and geological structures, with implications for the origin of life and the formation of minerals, as well as to the manufacture of new materials. He has led the ERC Advantage Grant Project Prometheus, and furthermore, he is a researcher committed to promoting a science citizens culture and an explorer of the frontier between science and art. I'm delighted to give you the talk, Juan Manuel, and welcome to the seminar.
Thank you. Thank you very much, Laura, for the presentation. Thank you very much to you also for the invitation to deliver this lecture in the CAP. I was planning to do this in person there and to meet the people there. I will be very much interested to meet several groups there in the CAP, but unfortunately we have to do this way. And in fact, I'm now in Bremen, so far from you. But let's do it in this normal way these days. Okay, so I will share my what is this? My screen. So hope that now is. Yes. You can see the screen, right?
We can see it.
Okay. Okay. So the lecture is about the role of silica in a lifeless planet. I mean, the role of silica in this planet before life conquered it. And so for that, I think it's important to see, I mean, the history of the planet. Basically, mostly for the people who are not very familiar with the history of this planet. So this planet is about 4.6 million years old. And 4.5, billion years old. And this is something that is very important to think about, because even for geologists, it's very difficult to grasp what this time means, because sometimes it's important when people say we're not talking about the origin of life and what happened in the early days of this planet. When people say, sometimes people say, well, yeah, you are proposing something that maybe this is only happened for 100 million years. And then people, so, you say only 100 million years. 100 million years is a lot of time. And so this is very important in order to understand what we are proposing, is to really grasp very well what geological time means. So I will talk about something that happened during the first billion years of the history of the planet, and what we call Hadean mostly, okay, but also in the Archean. This is the classical view that we have of the Hadean. It's a view in which, during the first 500 million years of the history of the planet, we call the Hadean because of the Hades, which is the god of the hell, because we thought until recently that the surface of the planet at that time was full of volcanoes, of hot lava, a very high temperature, a strong meteoric bombardment, an actual hell. And this is where the name came from. And a hell in which there was no chance for life or even for prebiotic chemistry. Okay, so this is a classical view until recently, but this has completely changed in the last 10 years. The reason is the evidence that we have found, I mean, a number of people of several groups in the world working with very tiny crystal of the Hadean time, crystal of zircons, because we had to remember that we don't have rocks from that time. There is no rock from the first, let's say, 300 million years of the history of the planet. The only thing that we have is zircons that are embedded in younger rocks that belong to that time. And people studying this zircon has demonstrated, and the evidence, I think, that is clear. I did not participate in all of these studies, but I was studying and talking with people who made it. And I think that this evidence is, unless something revolutionary happens in relation with the technology of isotopic studies, I think that this is an evidence that we host for many years, okay? So they show that 4.4 billion years ago, okay, just after the formation of the moon, there was already water, condensed water on the surface of the planet. And this is very important because if we have water condensed in the planet so early, I think that everybody agree that the crust at that time was a crust mainly made of ultramafic rocks, I mean, rock containing magnesium iron silicate. And this is well known, and these are experimental facts, that when you put in contact olivine, pyroxene, ultramafic rocks with water, then you trigger a reaction called serpentinization. And in this reaction, one of the gases that you form is hydrogen. So it is something that is unavoidable, that the planet at that time was basically a big machine, a big factory of serpentinization reaction. So we will have the production of hydrogen, molecular hydrogen, okay? Also, we will have the alkalinity of the water, so that the water at that time should be most probably, because of this reaction, an alkaline water. So in addition, the existence of hydrogen and the CO2 also at that time releasing from the planet, then we'll have the triggering of FTT reaction, that forming aromatic hydrocarbon and fatty acids, which are produced by this type synthesis. So that we will have a number of molecules directly related to the serpentinization. And in addition, as I told you, we will have an alkaline ocean or alkaline sea that we don't know exactly how will be, the condensation, how the water was pooled at that time, right? But for sure, the water condensing should have a very high pH. And if the water have a high pH, then silica, is very soluble at high pH. The solubility of silica is basically about 200 ppm until pH 8.3. But after, a higher pH, the solubility of silica increases dramatically, exponentially. So to have a pH 11, you can have 4 or 5 grams per liters of silica dissolved in the water. And the speciation will depend on pH, but basically first and second deprotonation of the silicic acid. So that at that time, we will have a planet in which will look like this, completely different than the classical view, in which we will have a surface in which is condensed water everywhere. You have the reaction of serpentinization reaction at global scale. Then we will have a high concentration of hydrogen, high concentration of methane, and an alkaline water. And as soon as the first granitoid start to form, which is most probably happened 4.4 billion years ago also, then we will start to have a silicification of this alkaline water. So this is the view that we consider for the planet. So for how long this happened, well, we don't know, right? But certainly will be a transition. This situation is a scenario that we are showing here is a scenario that will change with time from high methane, high hydrogen concentration to high CO2 concentration. We don't know for how long, right? But certainly will be for a couple of 100 million years. And this is time enough, to really consider that the reducing atmosphere and alkaline pH and high silica concentration was working at the early days of this planet. Why silica is relevant and why it's important? Relevant is because silica is ubiquitous in the Earth, particularly in the Archean. If you study Archean rocks, you will see that all the Archean rock is silicified. So it means that at that time there was we need to have a scenario as the one we have already shown, in which there is a very high mobilization of silica. And the only way to have a high mobilization of silica is to have high pH. So this is why this is one of the ideas supporting, our view. So silica is ubiquitous in the air crust at that time. And the other why is important, not only relevant, is important because at high pH, silica have the ability to produce two different kinds of self-organization phenomena. The first one is biomorph. These are something that happened between pH 9.5 and 11. And as soon as you have the formation of, you have CO2 in the environment, you have the formation of carbonate and self-organized structure forming because of the chemical coupling between silica and carbonate, forming this structure that you see here. So there's very biomimetic structure that I call it silica carbonate biomorph. These are, as I told it, self-assembly nanocrystalline aggregate, which display continuous curvature, either positive or negative continuous curvature. And therefore mimic very well the morphology of early life. But also not only the morphology, also mimic remarkably well the texture of biological skeleton. So that in a way in which silica is replacing the role of organic molecules in biological skeleton. So these are some factors related with the properties of this texture or morphology. So the interesting thing, well, this is a nanocrystalline material. I don't want to go into the details, but interestingly is that if you remove, as you can see in the video in the lower right part of the screen, you see that the removing the carbonate will maintain the morphology of the crystal aggregate because there is a silica skin, so that you will have the same morphology, a phantom of the same morphology with a silica made of silica, only made of silica. So how this morphogenesis, how this occur? Well, it's occur basically because two main roots. The first root is a fractal root, so everything starts with a single crystal of barium carbonate or calcium carbonate or strontium carbonate, in which as growth occurs, there is a poisoning of the crystal faces by silica, so triggering what we call a fractal branching. I mean, a branching without crystallographic control. And this gives this morphology that look like a cauliflower, typical fractal structure that look like from outside a globular structure that is a very, let's say, very biomimetic morphology for early organisms. Later on, upon this fractal stage, we have what we call fibrillation, in which the crystals are not only growing, but in a certain moment they start to have nucleation. So you have nucleation of calcium carbonate that are inhibited by the poisoning of the silica, so that the crystal cannot grow, then you have just a coating, avoiding the growth and maintaining the size of the carbonate crystal in the nanoscopic scale. You have continuous phenomenon, and then allow this structure to form sheets which are developing in two-dimensional way, in which you have the nanocrystal of carbonate co-oriented one each other. And in principle, if this grows simply by two-dimensional growth, radial growth, then we will have the formation of this. The point is that when this crystal structure, these morphologies are forming, as you can see here, there is some point, singular point, in which the structure, which is radially grown, then start to curve. So it's just curling the structure, okay? And this is the mechanism, behind the morphogenesis of very complex structure. I will try to explain. Actually, this is the curling of the structure. So in some point, the curling structure. So it's grown radially, but at that point in which the structure curls, there is no way to continuous radial growth. And then what you have is a propagation, like a surf wave, in the sea, a propagation of the curling, along the rim of the structure. So that if you have two single points with counter propagation, then you will have the formation of leaf structure. This is one of the origin of the curvature. So actually, if we consider just three parameters, the chirality of the curling being left or right, the degree of curvature of the curling, how large is the radius of curvature, and then the velocity of the sheet and the velocity of the propagation of the curling, we can explain all the structure that we have observed, all the morphology that we have observed. For instance, here on the left, this formation of this leaf or cardioid-like structure, in which you can see that you have the curling propagating. Okay, the two of the curling are up, so one is left and the other one is right, and then they just meet, and then the growth stop. But if you have the curling of the same chirality, both left or both right, so one up and the other one down. So what happened is, you can see in this video is that you have the upper one which is up and the lower one which is down, and then they meet, okay, and then they form the twisted ribbon, one of the characteristic morphology of the biomorph and also the characteristic morphology of the early life. Then if you have exactly the same condition, but the propagation of the curling is faster than the formation of the propagation of the sheet, then what you have is the formation of this bread, okay? And exactly the same one, but if the radial curvature of one of the curling is much higher than the other one, then we have the formation of worms, and you can see in this video here. So this mechanism is we can explain with this mechanism of the kind of morphology, and actually we have already shown that depending on the morphology and the supersaturation of barium carbonate, depending on pH and the supersaturation of barium carbonate, we can explain, all the panoply of morphology and the variety of morphology of silica biomorph, so that we can use this also as a geochemical proof, for this. Now, interestingly, we have also made this with calcium carbonate, and actually we are now know how to control the morphology and texture of the calcium carbonate biomorph, so that this is very interesting advanced material, but also is very interesting because for now we know that not only aragonite but also monohydrocalcite are able to produce biomorph and wonderful structure, the one you can see here in this slide, the work performed by my former student Gan. So the chemical driving force, why this happened? Well, this happened because we have the reverse solubility of silica and carbonate and metal carbonate with respect to pH. So that if in the growth front of this structure, you have the precipitation of carbonate, they will produce a decrease of pH. And because of the decrease of pH, the system will be supersaturated with respect to silica, so that we will produce the precipitation of silica. But the precipitation of silica, they will produce the increase of pH. So we have a self-feeding mechanism that is, explaining and happening in the growth front of this structure. This is something that was very difficult to demonstrate, but with the help of technology developed by my colleague Marco Montalti, University of Bologna, we were able to measure the pH in the growth front with a resolution of 100 micron, and then we're able to show that this is what actually happens. So what we have is an oscillation of pH in the growth front, and which is this chemical coupling is the one is behind the formation, the chemical reason for this formation of this cell assembly structure. Now, why this is interesting for primitive life datation? Well, the reason is because the criteria used for primitive life datation are basically four. One of them is the morphology, isotopic signature is another one, chemical composition of the carbon acid compounds, and then we have another thing, stromatolitic structure, that are a structure where they are not actually fossil, but the structure made by biology. Okay, so but isotopic signature and chemical composition have several problems. So the still morphology of putative microfossil, I mean the structure found in the oldest rocks, all the sedimentary rocks, then morphology still is something which is very important. I would say the main proof for demonstrating evidence of early life. The problem is that the reason why morphology is used, and actually was used, but now most people, I think that now accept the morphology is not a good criteria, unambiguous criteria for life detection, is because people consider, that there is two worlds of symmetry, the symmetry of life and the symmetry of the inorganic world. And then it was supposed that when you have something which is very complex in shape, is something that the inorganic world will not able to produce. So that, for instance, these are microfossil structure proposed, and most probably they are, microfossil structure that contain morphology to consider to be unique for life. But you compare this morphology with the biomorph that we grew in the laboratory, you can really there is no difference between them. This is the ability of biomorph to mimic the morphology of early life is amazing, as you can see here in this one. But it was not only the morphology. The point is that the condition and the which, because all the structure proposed to be microfossil in the early rocks are found in chairs. Chairs is silica. And some of them are actually the oldest one, all the proposed one are Precambrian chair with barytic chair. So in which you have barium. Barium is one of the structure, actually the most important elements of carbonate, barium carbonate producing this biomorph. So it means that the condition in which we are growing synthesizing the biomorph in the laboratory are very similar to the condition in which form the rocks containing the putative microfossil of Precambrian times. So then we said later, because there was another important character of the proposed microfossil structure, which is the organic compounds. Okay, so what we did is to cook the biomorph in mixture of phenol formaldehyde. There's some material which are supposed to be easily in the early earth, And then we cook this with 350 degrees to make the kerogen, and then we compare the Raman spectra of the microfossil made structure in the laboratory with actual proposed microfossil, and we cannot distinguish the Raman spectra of both laboratory made and natural microstructure formed in Precambrian rocks. So what we claim is not that these microfossils are not microfossil. What we claim is the morphology does not contain equivocal genetic information. This is what we're claiming. Okay, so that looking for primitive extraterrestrial life detection cannot be only based on morphology. We need to have a textural study and also chemical, particular isotopic study and nanoscale is mandatory. So some people, told me, well, but Mama, you say the morphology, so it's not a character in biology. So what happened? You see a ammonite or a dinosaur. It's not morphology. It's enough to know that this is a fossil. Well, the point is that it's not morphology. What tell us that this is a fossil? It is actually something that we forgot in this comparative anatomy. Was it the Baron de Cuvier who made in 19th century, right? So it's actually the comparative anatomy who tell us that this is a fossil. You can read this wonderful book, Lionstone of Marrakech, which is Stephen Jay Gould. He was, because the Marrakech, there are many fossil, ammonite, belenite, beautiful one, and the Moroccan people developed a wonderful technology, to make them. So that most of the fossils that you can buy in Morocco are made by Moroccan people. So, and then Stephen Jay Gould was studying, how to distinguish, but because the morphology is the same, but the important thing is the character that telling you that there is a comparative anatomy, there are functionality, between the different part of the fossil. And this is very interesting. The problem of primitive light detection is that there is no complexity enough to apply comparative anatomy. So we have very tiny organisms, with just one cell organism, and the morphology that we can have a very simple morphology. That morphology that can be made by several physical and chemical processes alone. So, and this is why it is so difficult to identify life only using morphology. I think that we need to use always a different set of technology. So the other self-organization process that happened at high concentration of silica and high pH is the formation of what is called chemical gardening, the formation of tubular structure. This tubular structure, this is one of them made, is a phenomenon relating buoyancy and osmosis, basically. And this is the formation of this kind of membranes, tubular structure, hollow structure, in which this hollow structure are made by the membrane of silica and metal oxide hydroxide. So we were developing this studying the formation of this structure. This structure were supposed to be actually live in early studies on the 20th century by different people. Stephen Leduc, Herrera, many different people were working on this, considering that was the time in which plasmogenesis, and plasma was very important before actual current biochemistry started. So people considered that was something related with the origin of life, because actually you can see the phenomenon is a phenomenon which includes osmosis, includes the formation of membrane, includes the formation of viscosity, which was considered very important for life at that time. Okay, but there is not really interesting from my point of view. The point is that why I became really interesting and see another way to relate this with origin of life is because we were able to demonstrate that you measure the different properties, of the phenomenon taking place in the formation of this structure. You see that there is a very interesting and complex flow of different cations and ions in the system. But the interesting thing is that it's created a potential, an electrochemical potential during the formation of this membrane. And this electrochemical potential, which is not insignificant, it's really interesting. So it lasts for almost 1 day. So that means that if we have this kind of structure forming in a laboratory, you have a battery there. And in principle, you can use the battery to trigger chemical reaction, including organic synthesis. And this is why this, to me, become interesting, this kind of structure. So now the point is, are these self-assembly mineral structure geochemically plausible? Because this is very interesting, very biomimetic, could be very interesting, but the point is that, well, you are working at very high pH and high concentration of silica. Is that possible? Well, in principle, you see that this is really, really possible. This is the condition in which we form the silica carbonate biomorph and silica metal oxide hydroxide membranes, so that you see that you need to have a high pH, high concentration of silica. And actually, this is something that now there are very few places in the world, but still there are places in the world in which you really can find this structure, particularly in serpentinization reaction areas, like the Aqua DNA in California, and also in Rift Valley, in carbonate-rich soda lake, like the Magadi Lake, all the lakes in the Rift Valley. So that we were there in this point, so we were collecting samples in these places in the world, several places in the world, and then we show that you take the serpentinization water, for instance, of Aqua DNA, which are a pH of 12 and a concentration of silica of 5 grams per liter. So it's being higher than the one we use in the laboratory. Then we can really show that you can make biocarbonate biomorph using this water. You can make the calcite structure, typical structure, very biomimetic structure, and also you can make metal silicate membrane with the water. So that in principle, this is something that it is possible. So, and certainly if we believe and we show and we can demonstrate that in the early Earth, there was this serpentinization was something happening at global scale, then most plausibly we have a lot of places in the world, not just few places that we have now, but at global scale, we will have the possibility to form this kind of structure and in the early years. Also, for instance, in Lake Bogoria, it's a Rift Valley with Melese Getenes performed this experiment, which showed that you can have formation of metal oxide membrane, not only made of silica, but also silica carbonate. Okay. Then there is an also very interesting experiment that we made years ago, and we are now performing under other circumstances and also with other metals. But the idea is the following: we just to mimic what happened according with our view in the alkaline ocean, from serpentinization at the early days. So as soon as you have granitic rocks, that should happen, very early, let's say 4.3 billion years ago, even 4.4 billion years ago, you will have this contact between the alkaline ocean with the granitic rocks. So what we made is to pass through an alkaline solution with a concentration of calcium, a high concentration of calcium, relatively high. And then we pass through a reactor in which we have a granitic rocks. And then we observe that just by passing through the solution, high alkaline solution containing calcium through the granitic rock, the formation of this chemical garden, this formation of this membrane, in this case of calcium hydroxide membrane, occurs. So it's something that should happen, at that time, just as soon as you have the interaction of alkaline ocean, high concentration of silica, high pH with granitic rocks. So this is, so do silica-induced mineral self-organization play in a role in prebiotic chemistry? So what is the role expected of this material? One of them I already showed is it is interesting, silica biomorph, particularly for the detection, understanding the detection of primitive life. But also what we have shown is that, the Miller-Urey experiment very well. It is an experiment that everybody know, because it's something was very, very famous experiment in which Miller, tried to emulate the early Earth using an atmosphere made of a mixture of reducing gases, and the ocean was water there, okay? And then the experiment was so simple, was very successful. Everybody, Miller and everybody later, the experiment was repeated many times, use a reactor of borosilicate. And then remember that the solubility of silica increased dramatically with pH after pH 8.3 and high. The point is that when you use ammonia in this experiment, the pH go to pH 11. So I was thinking that maybe, this is silica could have a relevant role in the formation of this experiment, in the result of this experiment. Okay, so that we made an experiment, 3 experiments using exactly the same atmosphere, the same electrode to mimic the electric discharge, supposed to be, the early Earth. And then we made one of the experiments in the borosilicate reactor, the other experiment in Teflon reactor, and the other experiment in Teflon reactor with pieces of borosilicate glass in the water. And the result was very dramatic. You can see here below, here you can see in the borosilicate reactor, there's a lot of formation of organic compounds, a lot of formation of solid organic compound. Actually, the reactor is covered is coated by a thin film of organic compounds. In the Teflon reactor, much lower concentration of organic compound, yes, physically. And in the Teflon reactor, plus pieces of borosilicate, there was a little more of these compounds, okay? And this is the difference. So we show that the most important and prebiotic compound resulting from the famous Miller experiment occurs when you have the borosilicate reactor. That means that borosilicate is a key piece in the result of this experiment. So the point now is to see what is borosilicate is doing. Well, in my opinion, and we are performing now experiment trying to have a better understanding of what actually happened, but it's seen not only from this experiment, but the other experiment that people just brought me, people are doing similar experiment for other kind of reaction, nothing related with origin life, but people is observing, is demonstrating that borosilicate reactor basically, most probably, just the formation of silanol group, because of the dissolution of the borosilicate, is the responsible for the successfully, some way the catalysis of this reaction. So this experiment, in our opinion, is an experiment that show that silica could play a very important role in the formation, the transition from inorganic geochemistry to organic geochemistry. We also perform experiment now using the formamide route. This experiment is much more simple. The idea is just to perform the condensation of formamide at 80 degrees, putting the formamide in solution inside a reactor in which we perform the silica garden experiment. This is what we did. You know, we use zinc, iron, copper, manganese, iron 2, magnesium, and copper. So to show the the role that this structure could have in the catalysis of the reaction. And then, well, these are the experiments that we perform using nanodrops of the saturated metal solution to do the more, let's say, clean, chemically clean experiment. And this experiment lasts for 24 hours. And later on, then we measure by gas chromatography with our colleagues, Raffaele Saladino and Ernesto Di Mauro in Italy. And then we show that actually there was a wonderful catalytic effect of the metal silicate hydrate membrane, basically membrane of silica and outer part of silica, inner part of oxide. And then we see that outside the solution, so where you have the silica, basically you have the formation of amino acids, outside, yes, amino acid, and inside the nucleobases. So this is what the result, the overview of the result that we have observed with the formation, the catalytic role of metal oxide, hydroxide, and silica on the condensation of formamide. This result, I think that very interesting, you know, and very clear. So that I think that it is reason to suggest, and we are now working on that, that silica plays a very important role at the early days of our planet. So we believe that for a while there was a planet in which the atmospheric and the hydrosphere were controlled by serpentinization. So that means that we have a reducing atmosphere rich in hydrogen and methane, and an ocean or a sea or pool, you know, that were basically alkaline and rich in silica. And I think that this scenario is a scenario that play a role for at least 100, 200 million years, which is enough to really create a wonderful variety of organic compounds. And now the problem, you know, is to know how these organic compounds are able to self-organize. We propose, and we are studying actually, you know, that the biomorph, either carbonated silica biomorph or silica membranes with metal oxide hydroxide was playing a very important role in the early Earth. Okay, well, that's all. I will also like to acknowledge the people, you know, there are many people who were working in this. Actually, we're a group that now from the University of Constance, Helmut Kolfen, the University of Bremen, Wolfgang Beck, and the APGP in Paris, Marwan Swilling, we have submitted a synergy, and we are working hard, you know, in trying to develop this idea of the role of silica in the early planet. And it's not something that we propose for the early planet, but you know, any planet of the like Earth, you know, any could be, you know, any other planet on the moon or even interstellar dust, in which you have basically olivine and pyrocene. You know, I think that it will be extremely easy to have organic molecule everywhere. Thank you very much for your attention.
Thank you very much, Juan Manuel, to you, because it's been a very, very interesting talk, at least to me. I would like to, before asking people to tell their questions, I have one myself. First, I just want to check if I understood it well. As I got it, I see it as silica. It's interesting for in terms of understanding early life, but in two ways I understood. One, these biomorphs, it's able to produce just physically. I understand this is like cheating us because it is not really life, right? It may look like that. And then we have the really connection to promote life formation because it sort of catalyzes the production of organic compounds. Is it right?
Exactly.
Is it these two views, right?
There's two views. One view is that you mimic the morphology of a structure that could be misunderstood with primitive life. This is one role. The other role is in the catalysis of a prebiotic reaction. Okay, so we were able, for instance, in this experiment with Miller and the formamide, we were able to make nucleobases, many amino acids, amide, dipeptide. So this really seems that silica, not only we don't know yet is how it works, but silica, I think that silica is playing a very important role in prebiotic chemistry and in the well, who knows, maybe also in the transition from prebiotic chemistry to life.
Second point is the one I'm more interested in because as we talked before the talk previously, I told you I work with biomarkers preservation in silica sinter matrices. And what really matters to us is the fact that these sinters are thought to be very preservative. So if you have some organics indicative for life enclosed in this type of matrices, it serves like a protection and preservation over time to keep your biomarkers intact. So this is sort of in contradiction, or maybe it depends on the silica species that it may promote or catalyze the production of organics, prebiotic organics, but other species maybe are more protective of these biosignatures. What do you think?
Well, you mean that silica is a very environment for preservation of organic. Yes, no, yeah. This is something that we are now performing an experiment with the Miller experiment, basically. So the idea is to conduct, reducing atmosphere. We are also working with transition from reducing to high CO2, high carbon monoxide ratio. But the idea is to perform the experiment in the presence of silica. So now we are working. So far we just mimic the experiment with no silica in the environment, just water. Okay, but now we are performing the experiment with silica. The idea is actually to know how silica is able to preserve the molecules forming in the atmosphere. In addition, because this experiment that we have performed, showing that the role of the reactor, the glass of the borosilicate glass in the gelding of the diversity, molecular diversity, and the gelding of the Miller experiment, I think is something important to realize how important were rocks at the very beginning. It's something that people normally have forgot. Actually, Miller never considered that. So he noticed that there is silica in the gelding of the reaction, right? But he did not realize that silica was key, for the experiment. So I think that it is very important now to perform an experiment in which you produce, mimicking, the early Earth, produce organic compound in the presence of silica, and to see how these organic compounds are preserved there.
Okay, thank you. I don't know if anyone has a question. I saw was a comment before in the chat, a comment from Jens Olmo. He said, I think useful hint to get a feeling of geological time is to contemplate that it, in average, roughly takes 300 million years for a sand grain to be deposited on the seafloor, get uplifted into a mountain range, and after erosion of this mountain range, end up on the seafloor again. In some geological contexts, this is considered a short period. I guess it had to do with your first introduction, or
yes. Well, this is basically mechanical, because what some people that there was for many years. Well, even now. So most people consider that the Miller experiment is irrelevant for the origin of life because he missed the atmosphere. Okay, because people say, no, the atmosphere was never methane rich at the very beginning. Why? Because this is something that is a criticism that was mainly made by Abelson and other people. When we thought, remember that until 10 years ago, we thought that the Hadean, 500 million years, the first 300 million years, there was nothing there. So there was nothing. So that people say the atmosphere already plausible, already relevant for origin of life was the, let's say, 3.8 billion. And that atmosphere was probably CO2, a high carbon monoxide. But the idea that we are now, and now every month there are new papers showing that actually was way. I have a problem with the. Sorry, it's no battery, almost no battery. So I have to move here.
These things happen.
Okay, now it's okay. So
is it only? Did you miss the?
I think
battery.
Yeah, I think he doesn't have any battery. I think let's wait for a couple of minutes and then see if he comes back.
Okay.
In the meantime, if you have questions, you can also write them down here in the chat. Yes.
Yes, we have one from David, and Hector had his hand raised.
Yeah. But I think he's going to write his questions in the chat.
Yes. Or you can.
Yeah, you can
ask it by yourself if you prefer, Hector. I think it's a matter of a couple of minutes. Whatever you prefer.
hello.
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 I'm back. Sorry about that. It's too late for the.
No problem. Go on.
Okay. So yeah, I was talking about the idea that we have of the early Earth. So it's now very important to realize that the criticism for reducing atmosphere that Miller used in his experiment is not anymore valid, because the scenario is incompletely. So it is clear that we don't know yet, how much time, but it was clear that we have serpentinization is a theory of serpentinization as a factory for the production of hydrogen, is a factory for the production of organic compound via FTT, is a factory for the formation of compound via electric discharge of ultraviolet, or just for meteorite impact. So there was for a while, we don't know what means this while, was a very long time, let's say maybe 100 million years. So this is enough from the point of view of chemistry. We are not talking about any sedimentary process, we are chemical process. We are talking just that for a while you have serpentinization working at global scale. And this will mean a huge production of hydrogen, and then a very high concentration of methane because of the interaction with CO2, the formation of organic compounds. So this is what I mean, in geological time. So it is nothing related with mechanic property. It's just related with the kind of atmosphere and hydrosphere that we have in the early Earth.
Mm-hmm. Okay, Hector, can you go on with your question?
Yes, hi. So first, it was a very good talk, so thank you. And my questions were related to Mars. Like, do we know if the early Mars had these conditions too? So these biomorphs could be formed in the neighbor planet also?
Well, in principle, this biomorph and silica-rich and the role of serpentinization is expected for any Earth-like planet, as I say, or Earth-like moon. So we know that Titan, for instance, have huge organic compounds. And that's where this could be mostly related with the role of serpentinization at that time. In Mars, in principle, it looked like the geology of the planet was very similar in the early time. Later on, what happened is that here we developed the tectonic driven by plate tectonics, but in Mars it doesn't occur. So I think that now that we have one robot and another one soon on the surface of Mars sending information of, particularly for Omnia Planum, from ExoMars, I think that we will have, let's see the possibility to have real data. The good thing of ExoMars, it is something very important. So I know that ExoMars is just looking for life, but for me, the good thing of ExoMars is that we are looking for real rocks in a window of time in which we don't have rock here on this planet. So it's fantastic for geologists. It is something absolutely wonderful. So we have two ways. In principle, what remote sensing and the data now obtaining from Mars say that serpentinization is seen to be working. There is a recent paper in Science about this.
So could we predict the shapes that these crystals would take in Martian conditions in order to compare with samples from Perseverance when they're back on Earth? Or
In principle, it could happen. Yes, it could be. We know also that there is silica in Noxia Planum and the near places there. So let's see.
Okay, thank you.
Thank you very much.
That'll be very interesting. And we have another question, Juan Manuel, from David Hotchberg. He said, do you know the reaction pathways that are operating in your Miller experiments carried out in the presence of silicates? I think you said something a little bit before, but.
Yes, well, we need to study more because you read the paper, you will see that we have no proof that is silica, what is really playing the role, because could be also the boron, okay, or the aluminium, but we proved that there are silica in the film, organic film coating the borosilicate glass. This is something very interesting. I mean, this is not a novelty. So we made the experiment exactly like other people did before, right? But we underline that the formation of this film means that you can make films triggered by rocks, triggered by mineral surface, organic film, directly from the raw material there. And this is something we had to take into account. For instance, now when explaining what we will find in Mars, so that if that is true, I mean, it's something like we mimic in the laboratory was happening in Mars in the early time. I think that any compound that we will find in Mars probably are from inorganic origin. Okay, so we have to consider this. And the reason that we consider that silica is playing a role with this, how this could be explained, is because most probably with borosilica, this is a glass that has been treated in order to be rather neutral. Unless it is known that you solubilize in alkaline conditions, and then what you expose to the surface and to the reaction silanol bonds, and we think that silanol bonds are the one really making the let's say the catalysis of silica, in making the experiment, I mean the experiment triggered by the plasma to the electric discharge much more efficient. But we are working on that. There are other reactions and people that, again, not really have a solid evidence, but many suggestions should be OH and particularly we are really playing as a catalyzer in this reaction.
Okay, there is someone else having a question? Yeah, we have it.
Yeah, hi, thank you.
That's cool.
For the very nice talk. So I have one question regarding your experiments with formamide. Then I was wondering what is the minimum amount of formamide needed for the experiments to get this chemical complexity of nucleobases and so on. And so what is forming formamide in the first place? How formamide is formed in the first place?
Oh, this is very interesting. Yes, very interesting. Well, the first one, we did not make a screening of the concentration of formamide needed for this, unfortunately. Well, I think it's a lot of work. Maybe, not for us, who made the experiment, but for the people who made analysis with gas chromatography, is painful work. But I think that this is not really important because, we made an experiment in which we analyzed the data in this following day, overnight. So, but it will be very interesting, as you say, to know exactly what is the role of the concentration and how this affects to the gelding. But the other point is important, is where is the formamide? Why is the formamide? Well, the point is that when you perform the experiment of Miller experiment, the cyanuric acid, as soon as it's in contact with water, then formamide is forming. So actually, in the Miller experiment, formamide is forming. And now there is a computer simulation in which it is clear, that should form. It seems to be a transient experiment, but it is clear that formamide it is now there is more and more experiment, proposing that the formation of formamide and solubilizing in water is something that should occur at the very beginning. Actually, I don't know this is Senni Shadow published a paper or not, but I know that they have the results in which they show that formamide, as soon as you have water, formamide is forming in this kind of experiment in the, but also in the middle experiment is formed. So, I'm very much in favor of the formamide route for the origin of life, but certainly to prove the geochemical plausibility of the formamide and the problem of the concentration that you pointed out, I think is very important. Thank you for the question.
Thank you.
Okay. So last minute for a last question, or we can just. I have more questions anymore.
Okay.
So I just would like to thank you for your very nice talk, Juan Manuel.
Thank you very much to you for the question and for the invitation.
Yeah, sure.
I hope to see you soon in Madrid.
Yes, that'd be great. Hopefully the situation gets better finally and we are able to have our speakers here. Thank you.
Okay, thank you very much. Ciao.
See you all in the next seminar next Friday.